Hi, this is Brian Nett with HowRadiologyWorks.com. Today we're going to talk about thicknesses of material that are necessary for a certain amount of X-ray penetration, and namely comparing different types of material. So if we say water versus bone, how much material would we need so that we had the same amount of X-ray penetration through, say, water versus bone? So if you're interested in this kind of material, click on the subscribe below. What we do is we have bite-sized content on how radiology works, and then click on the little bell icon if you want to get notified when we release new content. So again, X-ray transmission, and we're comparing different materials. So that's what we're going to talk about today. So first we'll just go through pictorially what we're going to solve for. Then we'll have a few equations. Don't worry, we'll keep it short, and you don't have to memorize equations or anything. And also, if you haven't watched the video we have on Beer's law, please watch that one first and go through that calculator first, because it's related to this, and this is just an extension of that, kind of taking that same Beer's law and saying, now we want to compare two different materials and see what their different X-ray properties are. So we're going to define one material as the reference material, and on our little X-ray calculator we can select what that reference material is. So say water, for instance, and then another material which is going to be our new material. And the idea is that we'll have the same incident flux coming in. So if you have the same I naught, or the incident flux of X-rays coming in, and we're assuming they're coming in parallel, and then we define for this case what would the thickness be as we come through to give the same output. So as we go through, the transmission, like we talked about last time, is just the amount that comes through divided by the initial amount, namely the flux of photons coming through. Like we said, the material itself in general is not going to be making radiation, so this I is always going to be less than I naught as we're coming through. And what we're going to solve for here is the thickness of the new material such that we have the same attenuation. So this just gives us a sense of, and I just said attenuation. Attenuation is the amount that's stopped in the material, and transmission is the amount that goes through the material. So if we have the same attenuation, we have the same transmission. So real quick, we'll just go through the equations quickly. Don't get scared by the equations or feel like you have to memorize them, but we just want to define first what the equations are that the little calculator is using, and then we'll just play around, so that the more important thing I feel like is that we get a sense of how the different materials compare to one another, and how those properties change as a function of energy, for instance, of the X-ray beam. So like what we said, the X-ray flux that's coming in is the same, so then we'll have the X-ray flux on the outside be the same. So the new flux and the reference flux will be the same. And like we said in Beer's law from our last lecture, we're going to have I naught is that incident flux, and then this is going to be a number that's less than 1. So it's the reduction in flux, and this is the reduction in flux of the new material, and this is the reduction in flux of the reference material. And this component here, this is mu over rho. This is dependent on the material and dependent on the X-ray energy. This is just the density of the material, so that's not dependent on the X-ray properties. And then this is the thickness. How thick is that material? So these mu over rho, and rho is just the regular density, mass divided by volume. And those are just, we can just look those up on the NIST website. And in our calculator, we've done that for you just to make it easy. And then we could just take this equation, just cross out the I naughts, and then we get this. And we see that we have the same exponential, and then these terms look similar here. And what we can do is we can take the logarithm of both sides. So if you remember from math, if you take the log of an exponential, those two things basically cancel out. So then what we'll get is we'll get just a linear equation. So we have, again, the mass attenuation, the density, and the distance of the new material. Then we'll just take these things, we'll divide both sides by these components here. So if we solve for x new, the thickness of that new material, given these other things, so we'll have an input that we say, what's a reference thickness that we're going to have of the material? And then all these other things are just from the NIST website. So the density of the material and the mass attenuation coefficients of the reference and then the new material. Okay, so we're done with equations for now, and we're going to play around on the calculator now. Again, the idea is that we have a calculator, and the purpose of that is to figure out if we start with one material and then we want to look at another material and say, how much of that material would I need to stop X-rays to the same degree? So if X-rays are coming through, to get the same level of X-ray transmission, or we could say the same level of X-ray attenuation in that single material. And the idea again is, say I live in Detroit, it's where I grew up, and then I want to move to, say, the Bay Area, and then I want to say, how much more money would I need to get in order to get a job and have a equal standard of living going from, city A, Detroit, to city B, San Francisco? You can go to these little online calculators. So this was the same idea, except for X-ray transmission instead. And so we have what we're calling the reference material. So that's like the first material. And then the new material. So let's start them out with having it be matched, equally matched. One thing I want to tell you is when we switch this energy level down here, that's going to set us back to kind of like a reference scenario. So anytime you go and you switch this energy level, switch the energy level first and then do your materials after that. And we have it that way just to keep the model simple, but basically we have to remember when we're doing this calculation that the X-ray attenuation is dependent on both the material and the energy level. So for this calculator, if you change the energy level, do that first, and then go and change the materials. So if we start with water and water, we have a thickness of 1. Obviously, we're going to have a thickness of 1 for the second amount of water because it's the same water. So now what if we take, instead of having water, if the second material is bone? Do I need more or less bone in order to stop the same amount of X-rays? The question is, do I need more or less bone? And the answer is I'm going to need less bone, right? Because I'm going to need less than 1/3 the amount of bone here, because bone is significantly more attenuating because it has that high Z material in it, right? So that's the first question. So this is about 0.3, right? Let's remember that number, 0.3 for a 50 keV. So now if we went to a higher energy, again, remember we changed the energy first. So we go to 0.8. It went back to water and water. Then we're going to change it to bone again. So we're water and bone. And now we went to higher energy. So now instead of 0.3, it's now 0.45, right? That's what we know, that higher energies are more penetrating, right? So that lower energies, if we remember, lower energies, if we want to make an image between water and bone, lower energies are going to have more contrast, and we want to use the higher energy beams in order to get that penetration through the object. So that's the first thing we learned, is that bone, we're going to need between 0.3 to 0.45, depending on the energy that we're looking at, of the same amount of material. Then let's look at something that's significantly different than that. So let's go back to 50 for a minute, and let's say water's our reference, and we'll start with water here, and then let's go to 100 millimeters of water. If we were at 100 millimeters of water, then we want to go from 100 millimeters of water and say something much more attenuating, right? So, for instance, lead. So how much lead do you think is going to be equivalent to 100 millimeters of water? Is it going to be 10 millimeters, 1 millimeter? It's going to be even less than 1 millimeter, right? So it's only 0.25 millimeters in order to get the same equivalence, the same amount of stopping power for X-rays with 0.25 millimeters as 100 millimeters of water. That's why we don't use water for stopping X-rays in our walls, in our doors. We're not wearing water aprons that are 100 millimeters thick, right? This is just the fact that lead has a high Z and it's dense. So both of those things are working in its favor for it having really good stopping power. And then what's on the opposite end of lead? So imagine, let's go back to reference of 1. For a thickness of 1, what's on the opposite end of lead? It's dry air, right? We're not talking about a vacuum, so there will be X-rays that are stopped within dry air, that ionize the dry air, but it's going to be significantly lower attenuating, right, compared with water. So if I start with 1 millimeter of water, what do you think? Is it going to be 10? Is it going to be 100 millimeters that we're going to need for dry air? It's going to be more than that, right? It's going to be 872 millimeters of dry air to get the equivalent attenuation of 1 millimeter of water. So at a high level, what we said is there's 2 orders of magnitude difference between water and lead, and then there's 2 orders of magnitude difference between dry air and lead. So there's 4 orders of magnitude difference between lead and dry air as far as the amount of X-rays that are going to be stopped in those materials. So let's just do one more just for fun. But in general, I want you to play around with the tool and really learn about the relative differences between these. So let's see if we go to fat. And if we go to fat, like we talked about, fat's less dense, right? Oil is going to float in water. So we're going to need a little bit more, right? A little bit more fat than we would water. So 1.16 millimeters of fat is equivalent to 1 millimeter of water in terms of the amount of X-rays that we can stop. So again, I hope you really play around with this tool. If you need CE credits, I hope you're using this to accomplish CE credits. If not, go to howradiologyworks.com/radcalcs, and from there you can find the calculators that we have. And we really appreciate your time. Thanks a lot. Again, this has been Brian Nett with howradiologyworks.com.